This lecture, we're gonna go over the exercise questions for chapter 9. Let's go started with the first question. The data in table P12 are weekly prices for IBM stock. Part A says, using a computer program for Riemann modeling, obtain a plot of the data, the sample autocorrelations, and the sample partial autocorrelations. Part B says, develop an appropriate Riemann model. Part C asks us to evaluate the adequacy of the model. And Part D says, generate forecast for the next 3 periods. And by the way, this is weekly data we have for IBM stock. So let's just move to Minitab right away to start our analysis. All right, so here's the Minitab data I have. We have weekly data for IBM stock. The main goal is really to estimate a Riemann model, examine the model, and then use the model to do forecast. To determine the specification of the Riemann model, we do need a time series plot, the autocorrelation graph, and the partial autocorrelation graph. So we're gonna start with the time series plot to see if the data is stationary or not. Let's get this time series plot. All right, so that's the one we have. One thing I want to point out is I don't really observe any seasonality, although we have weekly data. We don't see the same pattern repeating itself again and again. But on the other hand, in terms of trend, I see a trend going up in general, although in the segment at the beginning, it is going down and there's several declines within this whole period. So the basic idea is still to get rid of the trend, take the first difference and see what we have from there. At this point, there's no need to obtain the autocorrelation or the partial autocorrelation graph because we've already determined we need to take the first difference. So let's do that. Then we can determine the specification for the Riemann model. We need to define this new variable. As usual, I define that as diff. We're gonna go to calculator. So we're gonna store the results in variable diff, and the expression comes from the function list. We are looking at differences. There we go. Double click on differences, and we want to take the differences of IBM. And I'm getting rid of the rest because we're taking the first difference. The lag is 1, which is by default. So click OK, then we'll get the first difference. We want to double check if taking the first difference allow us to get rid of the trend. So we're gonna do another time series plot using the difference. Click OK. So based on this new time series plot, I can tell that there's no trend, at least based on my judgment. I don't see a trend there. At the end, it's going up, but that's just 1, 2, 3 observations that can't confirm an upward trend in comparison with all of the rest observations. Okay, so we're good with the first difference. And now we're gonna obtain the autocorrelation graph and the partial autocorrelation graph to see the specification for the AR part and the MA part. And remember, we are looking at the diff series. We don't use the original one anymore. Okay, so the series is diff, and here we go. Looks like that. That's the autocorrelation function. Let's go ahead and get the partial autocorrelation function. So here's the partial autocorrelation function. Look at this. Now we need to determine which one is cutting off, which one is dying out, right? In this example, it's actually clear for us because when I look at autocorrelation function, I see the autocorrelation is dying out. It's decreasing gradually and then becomes negative and increasing negative and dying out. Now in comparison for the partial autocorrelation, I can tell it's cutting off right at leg 1. This tells me autocorrelation is dying out and partial autocorrelation is cutting off at lag 1. And therefore, the specification for the model should be ARIMA 011. It's an MA1 process. Then we're gonna go ahead and estimate the model. So we go to Stat, Time Series, ARIMA. We're gonna use the original time series data because when we estimate the original model, we'll automatically take the first difference if we put 1 for difference. And we're looking at an MA1 process, so the specification will be 011. At the same time, let's obtain the residuals so that we can check residual for adequacy. Click OK, now we got the model. Mean square is 35, which is good, at least based on several models we've estimated so far for chapter 9. This MS definitely is a small one. All the p-values are higher than 5%, meaning there's no significant autocorrelation in the residuals, which is good. And furthermore, we want to look at the autocorrelation plot for the residuals. So I'm gonna do the residuals autocorrelation graph here. And by looking at this graph, all of the autocorrelations are within the red curves. They're not significant, meaning that the model is adequate. You might argue that for this lag, which is lag 9, it is slightly touching the red curve. And I agree with you. There's a tiny little gap, but it's almost touching it. So it's at the border. That may suggest something. However, when I look back at the Fox-Pierce chi-square test statistics, since I observed that all the p-values are substantially higher than 5%, I would say what we observed in the residual will not be a major concern for us. And therefore, moving to the last part, we're going to focus for the next 3 periods. We could have done that when we estimate the model. However, since we don't know if the model is adequate or not, it's probably better that we do it this time. So we're going to go to focused, and the lead will be 3 because we want to focus for the next 3 periods. Click OK, OK again. Got the forecast. And also the 95% limit are provided as well. So that's the first question. Let's move to question number 2.
Well, question number 2 says the executive director Marv Harnischberger concluded that the most important variable that consumer credit counseling needed to forecast was the number of new clients that would be seen for the rest of 1993. Marv provided Dorothy Mercy with monthly data for the number of new clients seen by CCC for the period from January 1985 through March 1993. Dorothy was very happy with your forecasting work so far. However, you are not completely satisfied. You tell her that she should try one of the most powerful techniques used in forecasting, the Box-Jenkins methodology and ARIMA models. Dorothy has never heard of Box-Jenkins, but is willing to have you give it a try. Question: develop an ARIMA model using the Box-Jenkins methodology and forecast the monthly number of new clients for the rest of 1993. So let's move to Minitab right away and start our analysis. Here are the data. We have the years, month, and number of new clients. And the data runs from 1985 until 1993. And the first step is to get a time series plot. We're gonna need to examine the data to determine if it's stationary or not. Then we'll go from there. So we'll do stat, time series plot. The variable is new clients. Click OK. And that's the time series plot. I can observe strong seasonality. At the same time, I can also observe an upward trend like this. And therefore, the first step is for us to detrend the data to make it stationary. Now, since this is seasonal data with monthly observations, we will need to do difference at leg 12. So we're gonna define the variable to be diff. Then we'll go to calc, pick calculator, and variable will be diff. Expression will be the difference. So double click on that. And we're taking the difference of new clients with 12 legs. So we do need to put 12 there. Then click OK. The new variable is defined. Now we need to examine the new variable div at the autocorrelation graph and the partial autocorrelation graph to determine the specifications for this seasonal ARIMA model. So go to stat, time series, autocorrelation. This time the variable is div, the new difference. And since we know this is monthly data, so we would need at least 24 lags, so we can look at 2 rounds of the seasons. Click OK. That's the autocorrelation function. All right, so immediately we see a significant correlation at leg 12. At leg 24, it is not significant. Let's take a look at the partial correlation function, then we can determine the levels. So we'll go back to stat, time series, partial autocorrelation, variable is diff, and we still want at least 24 lags. Click OK. And this is the partial autocorrelation. We would notice that this time for leg 12 and leg 24, both of them are significant. All right. So if we compare the autocorrelation function and the partial autocorrelation function, we can decide that for the autocorrelation function, it is cutting off at leg 1 because, or leg 12, because leg 24 is insignificant. Okay. For partial autocorrelation, we will say it is dying out because for leg 12 and 24, both are significant, but leg 24 is lower than leg 12, so it's dying out. And therefore, the model we're gonna be looking at is an MA1 process. But remember, since we took the difference at the seasonal lag, we have an I1 process as well. And therefore, putting everything together, we have an ARIMA. At the level, we have 0, 0, 0. But for the seasonal level, we have 0, 1, 1. So that's our ARIMA model to be used. Now let's fit this ARIMA model. So we'll go back to stat, time series, and pick ARIMA. We will use the original data. Make sure you check fit seasonal model. The period is 12 because we have monthly data. For the seasonal component, we will do 0 for autoregressive, 1 for difference, and 1 for moving average. Let's go ahead and obtain the residues because we will examine the residue as a check. So click OK. OK again. And that's our ARIMA model for the seasonal data. The criteria we're going to look at is mainly the p-value. All of them are higher than 5%, which means there's no autocorrelation in the residues, so it's passed. Mean square is 386. So far, the model seems to be good. Next, let's check on the residues. So we will do time series and go to autocorrelation. And this time we want the residues. Click OK. Now, by looking at the residues, we don't observe any significant autocorrelation, which is in accordance with the p-value for the chi-square test statistic, and therefore we can conclude that the model is adequate. So in terms of doing forecast, we can go ahead and use this model to forecast for the rest of 1993. If we go back to the data runs from 1985 and to 1993 for the first 3 months. So we will be forecasting for 9 periods or 9 months. And therefore, we're going to go back to stat, time series, ARIMA. And click on focus. We will do 9 period. So put 9 there and click OK. OK again. Now I've got the model again, but this time we will see the forecast for the rest of 1993. All right, so that's all the analysis we have with the Minitab. In terms of answering the questions, I will probably say the following. So by examining time series plot, we noticed trend and seasonality. Therefore, we take the 12. Therefore, we take the difference at lag 12. For the difference data, we decided that the autocorrelation is cutting off and the partial autocorrelation is dying out. Therefore, we have an ARIMA 0, 0, 0, 0, 1, 1 with subscript 12 process. And with all the answers, I would definitely include the time series plot, the autocorrelation function for the difference, and partial autocorrelation function for the difference. Then, in terms of the ARIMA model will fit, we'll say for the seasonal ARIMA model estimated, we find that all p-values for the chi-square test is higher than 5%, suggesting that there is no serial correlation in the residues. Also, the residue ACF shows no significant autocorrelation. Therefore, the model is adequate. So apparently, there are a couple of typos that I cannot fix after I moved it. At the end, what's said here is therefore the model is adequate. Now, in terms of forecast, I will include the forecast in my answers, this table in particular, and mention that here are the forecast for the rest of 1993 together with the 95% limit. All right, so that's all I have for this exercise. Email me if you have any questions.